My topic today is sustainability in software engineering. This is part of a course on sustainability in computer science. I would say because most of the, um, let's say, parts that you have heard about are also dealing with software engineering because software is basically the part that is required for implementing every functionality. My talk is on one side central, on the other side, of course, on the core of guaranteeing sustainability in here. However, I will hopefully distinguish from other speakers you have heard before, and you will also listen to next week as well. I will in particular focus more really on the software engineering part, and not on software that can be or should be or shall be done for improving sustainability in general. I also have not so many figures in there about showing you the importance of this topic because I thought that most of my colleagues have already focused on that. So I will try to at least um, tackle this question about sustainability from hopefully from a different angle in here. Before we start with the content, I have also prepared some motivational slides. I hope at least it is there. So to set up the area we are discussing in the next 42 minutes, 43 minutes. And afterwards, of course, I'm open for taking any questions. So the motivation is as follows. So of course, every one of us hopefully knows how software looks like, or how software looks like is maybe not the right thing here, but how programs look like. And sustainability is often reduced to energy consumption or to reduced energy consumption and maybe other resources, but mainly everything deals with the energy consumption. We see that this very prominently these days with ChatGPT and with the requirement of relearning, which costs a lot of energy, and the major players around they are thinking about installing power supply or power plants in addition to let's say increase at least sustainability in here. Um, so a lot deals there with sustainability in terms of improving algorithms, improving things so that they are more sustainable. In software engineering, of course, when we consider programs, we know that also the energy consumption depends on the programs, which means on the running software, and of course on the hardware as indicated here. So we have always these two things here in parallel. And I will give you one example that is, I think, quite nice and obviously showing maybe challenges and maybe also some ideas of how to improve that. So here is a function is element that takes an arbitrary variable that holds any value, and basically it should deliver true if this element we are passing to the function is in a list or in a collection in general, let's say it that way, and false otherwise. So it's a very simple function. Usually, let's say newbies in programming have to deal with. There are many ways of implementing that. The simplest way is we assuming that we have the collection which is capitalized A in this program, so the simple program, and then we are going from 1 to the length of A or from 0 to the length minus 1 from A, and check each element in here. Okay, so this is especially required when we don't have here any further information like sorted collections or whatever. And then, of course, for each element, we check whether there is an equivalence in here. And if yes, then we return true and otherwise false. Obviously, this has a complexity, a time complexity of O(n), where n is the length of the collection in here. And unfortunately, in this case, we cannot do better. On the other hand, a similar lengthy program also is element, but this time we assume that there is a hash function, and people who know what a hash function is knows that this can be more or less checked in order of one, because the hash function is giving us the index where the element is stored, and so we only need to say, okay, it's a little bit more complicated when we have, of course, there might not be a hash function that always points to the right element, and we need to go through a list here as well. But usually that's quite simple. So here would be the most simple approach. We only check whether A is equivalent to this hash value of A. If the element is not in here, then at this position there might be a null or anything else that indicates that this element is not stored. If it is equivalent to A, then we return true, and otherwise we return false. And as I said before, we can solve this in order of one. Why is this of help for sustainability? Of course, if it is of order of one, then there is not so much, how to say, energy necessary. Of course, and here, if you're carefully looking at that, the problem is with the hash function. If the hash function is very much complicated, then maybe we lose here a lot of computational resources, which belong basically to the energy consumption in here. But if the hash function can be done quite simple, then obviously I think we agree on that. The right program is more efficient than the left program is, and I'm assuming here that the number of statements we have to execute is more or less, let's say, in line with the energy consumption we need. Of course, this thing here is a little bit more complicated in practice, because we are not running the source code basically. We are running the compiled code, so we need compilation here as well, and then we get something like this and that for both functions. This is of course not complete here. It's for a particular architecture. I think it's for Intel CPUs, when I remember correctly. And those programs here in the front, the one I'm marking here and the other one, they are then executed on the computer. And of course, if we are interested in the energy consumption, we need to compare then the resources, the energy or whatever in here of those programs after being executed. So this is the thing we need to do. So what we see from this example is it's maybe not that easy. First of all, the hash function can be quite complicated. So when I go into this program, so first of all, we have here always the data that is in here. In this case, it's integer, but can be easily changed. Of course, if this hash function is complicated, then it may be a problem. As I said before, a problem, it may consume more time. If this can be implemented very quickly, then of course we will win with the right program, because it's only passing once through all the statements, whereas the other one has jump statements in here and jump on negative and all these things. So it's iterating basically until it finds the way. Of course, when dealing with is element, it does not mean that we always have to go through the whole list. We have to go through the whole list either when the element is the last in here, or when we cannot find it anyhow. So in all these cases, and usually we are considering here an average case. But it's a little bit more complicated. We need compilation. We need, of course, here then the machine code, which can be itself optimized, and so really stating that one program is more more sustainability with respect to resource allocation may not be right, and we will see also that compilation. Of course, it's also a process that requires a program, has also an influence here on the um, on the overall sustainability. In addition, of course, it would be possible to make programs that using a lot of libraries that themselves may depend on other libraries that are very, let's say, leading to a very complicated assembler program then, or machine language program then, where execution takes longer than expected. Since sustainability has also different, let's say, facets. At least resources are one, but the other one is maybe to say, okay, that the program is used. So maybe taking care of libraries is a good idea, but with respect, when we only focus on resource allocation, it might not be the best. So this was more or less the motivation, and we are now discussing those different things here in a little bit more detail. In particular, what we are going to focus here is runtime energy consumption. Of course, then there is a need for measuring that. I will come back later to that. And unfortunately, this is not all. And so therefore, we come to the objectives of this short presentation of today. So in particular, what my talk is trying to do is to answer the following questions. One is, why does sustainability matter for programs and software engineering in general? What is sustainable software engineering? Because this is also not that clear, and we should at least fix that to some extent. And so this is a contribution of today's discussion. And of course, then once we have fixed this thing here, the question is, how can we support sustainability for software engineering purposes or in software engineering processes? I want to note that the focus here is on software engineering and not the use of software to improve sustainability, and we'll come back to that here also in a few slides, but the focus is here really on the software engineering part, which is not often the case. What distinguishes software? I have no slide on that, but I'm giving, of course, here always introduction lectures at my university in Graz. And the question is always, what is the difference between software engineering and programs, or what is the difference between software and programs? And the answer is easy. Programs are part of software, but software is more also comprising things like test cases, documentation, requirements, whatever is here part or is here an artifact that is generated during this engineering process around. And this is the difference. In many cases, we are only focusing on programs, but in general, software is more than that. And software engineering is, of course, more than programming on that. And this explains partially, at least, why people may have different views when we talk about sustainability in this area. That's only one comment from my side on that topic in here. Okay, sustainability in software. So why it is important? Here we can have more or less two or more than two reasons behind that. So first of all, software is becoming increasingly important. I hope everyone here agrees. For example, in areas where software engineering was not that important, for example, in the automotive industry, there are many studies around, some of them starting earlier than 2022, showing that there is more and more functionality in cars that is only because of software. And some people are in the automotive industry nowadays, saying that a car is nothing else than a yeah, a mobile phone, a smartphone on wheels, which means basically that we have very similar situations than with all other systems. We have something, sensors and actuators around, and the software is implementing the basic functionality in here. So this is one thing. So software engineering is a central part of computing these days, and software will become more and more important in here as well, in all the areas, I have to say. It's also interesting, and this is the only real figure here, that ICT in general accounts for about 2 to 4% and maybe more these days with ChatGPT. I haven't checked that. These are the figures I found last year, but I think it's not becoming better in here. So that's 2 to 4% of all the global greenhouse gas emissions. And when you consider software as the backbone, then you see that software is here also a problem, or part of a problem we need to tackle in a holistic way, and not only considering one or two aspects in here. As a consequence of those nodes, of course, developing software that has a low energy footprint, the software and as well the development, we can save greenhouse gas emissions, and this is something we want to have in here. As I said, this problem is a little bit more complicated because greenhouse gas emissions, energy consumption comes also from the software development cycle. When we are often compiling programs, then of course we have to run a compiler, which of course needs energy. So maybe we should think more often before we run a compiler. Or if you have an interpreted program, we have the same. So we have a lot of repetitions in running programs until the program is then shipped out, deployed to the customer or the users in here. And then, of course, sustainability here means also that this program should be there for longer, because when you develop a new one, you need again greenhouse gas emissions for the development cycle as well. So this is the general problem we face in here. It's also interesting that this Brundtland report defines sustainable development as the ability to meet the needs of the present without compromising the ability of future generations to satisfy their own needs. And I think in software it's also quite clear, because on one side we want to have here software that is used, that is not contributing to things that negatively impact future generations in any way, not only about greenhouse gas emissions, but maybe also other ways in here. And that basically should then lead to a more sustainable society, economy, and of course the environment too. And but it's I would say, a complicated problem we have to face in here when we only focus here also only focus on software engineering. It's in general not an easy problem, but here it becomes even worse, I would say. When we want to, let's say, focus on defining sustainable software engineering, of course, there are many big players in here talking about that topic and trying to define that, including Microsoft. I'm not sure whether they changed their definition, but I said that slides from last year, and even in the case they change it, I think it's always worth looking at previous definitions. So Microsoft defines sustainable software engineering as an emerging discipline at the intersection climate science, software, hardware, electricity markets, data center designs. So we see also that the execution has here an impact, which is, I say, quite important. And of course, It's not formally defining that when you have a look at that, but the principles of sustainability software engineering are the core set of competency needed to define, build, and run sustainable software applications. So they identify at least that there is a need for also taking care about this as maybe as a additional requirement that has a huge impact on development, but also of execution of software, which is in here in this definition. There is also Forbes article defining sustainable software engineering, and in this case, maybe focusing more on the development aspects that this is popular at the moment, and that it aims to design software that will increase overall application efficiency, reduce energy and space consumption requirements. So it's here defined more from a technical perspective, reducing energy and, of course, other resources, because resources have always to do with energy and with greenhouse house gas emissions. So, for example, the memory footprint of a certain application, of course, has an impact also on climate because we need to produce the memory integrated circuits as well. So also this here comes not for free, even in the case it's cheap, but it requires resources, and the question is always whether this is really necessary or not. But the answer, of course, is not always that easy to give. Here are some other definitions, and we'll come then to a summary of that. Anyhow, also other definitions, and this is from a GreenSoft model we are considering a little bit later on in more detail. It's saying sustainable software is software whose developments, again, deployments, which means basically the way it is transferred to its use and usage, results in a minimal direct and indirect negative impact or even positive impact on the economy, society, human beings, and the environment. I think this is a very general definition, considering all aspects of software from the development to its use, and is therefore I would say, a quite interesting thing. It's a more technical definition, but definitely a good one. What are the prerequisites of sustainable software? Of course, the sustainable development process, and here, and therefore it is mentioned in this paper, of course, here the authors come up with such a process that considers environmental and other impacts during the software life cycle and development life cycle in here. And so therefore, sustainable software engineering is then the art of developing sustainable software through a sustainable software engineering process. And this is more or less than the general definition that is in here. It's, of course, a discipline that is on intersections of different fields, as we have already mentioned before. There are many dimensions of software sustainability. Due to time, I will not go through all the dimensions in here in detail. I have to say, so I think most of this is quite clear. There is on one side human sustainability, which encompasses topics like labor rights, psychological health, social support, social equity, livability, and all these things where humans are involved in. And therefore, of course, sustainability should also come or consider that at least to the extent that helps people. There is the economic sustainability, what I briefly mentioned in here. Of course, everything here is an investment. When we come up with a program, it does not necessarily mean that there is money flowing, but everything is an investment. We always take resources in here, and therefore, of course, what we finally get should meet the requirement, should be useful, should be good software, should let's say be developed in a way so that it runs for a longer time, and to assure that basically the investments in general are then, let's say, at least compensated during operation. And this is what we want to have in here. And the last thing is here the environmental sustainability that basically says, okay, we want to have an software green ability, which means basically that the software, including the development, but also then the execution, has no or has the least necessary impact on, um, let's say, greenhouse gas emissions or any other thing we want to reduce in here. So this is basically the dimensions of this software sustainability. And of course, a software lifecycle process has to consider these dimensions, basically. When we talk about green, the goal of green in software engineering, it's also quite an interesting topic. There are many facets around, and I don't want to go into detail about the text that is written here, but about the figure that is in here. So there is, I would say, not a general agreement what green software really means, basically, because it has two interpretations. One is green in software, where we can distinguish the software engineering, green in software engineering to improve the software engineering process so that it requires the least amount of also environmental resources, and of course, the product as well. And then, of course, it might be also other green aspects in here. For example, when we run the software, we can do that on a server that may has a bad footprint, or we may run it on a device that is very small with requiring not a lot of energy and all these things in here. So also these aspects need to be taken into account. So this is the focus where we are today. And the second part of green software is green by software. And I guess you have heard about that also in previous talks, where we use programs, software, ideas that are formalized in software or implemented in software in order to make our life finally better, more sustainable. And that's green by software. So we are in this presentation, we are ignoring that, and we are more focusing on the green in software part. To summarize the discussion so far is, I think, quite easy. In a closer sense, software sustainability is captured green in software, focusing on development, maintenance, of course, of software, and of course, not only on maintenance, but what's in here, but also the energy consumption of software during operation, in order to contribute to a reduction of greenhouse gas emissions. So this is the thing we have in here. And reduction during development means basically reduce compilations, for example, minimize relearning in case of machine learning-based software applications, and other things we may want to do. This can be supported by the process to some extent, so that we minimize things in here that we may think before we compile or use things, try to adapt also the development tools so that they fit the purpose in a more ideal fashion and so on. So this can be done in here during development. The second part is then reduction during use. So develop programs that have a minimized greenhouse gas emission footprint. For example, it might be what I said at the beginning, we use better data structures in order to reduce runtime, which in many cases reduces also then the overall executions in here. That's one aspect. The other aspect is, of course, that we use only the resources, the computational resources required to run the program, and not a huge server with a huge available memory. when it is not needed, and other aspects in here. So this is the use and the reduction of use to do that, or to optimize the executions accordingly, to adapt that maybe also the functionality to user needs and all these things in here. So that's basically how we can go in that way. There have been several publications. I should repeat this investigation. Maybe I will do that for the next year. What we see basically is that there have always been a peak on a number of publications. So one study is mentioning that in 2011. In the other study, it's a mapping study, where the other one is a systematic literature review, has more or less something like in 2015 a maximum. So what we see here is that those studies indicate that more or less between the first and second decade of this century, we have had a peak on that, and you will see it in my final slide, because I'm talking then about one of the workshops dealing with green software, which is now again running, that there is now again an increasing interest in this topic domain, and which I personally believe is also a good thing to have. I also said that there are models for sustainable. So the rest of my talk, and I had to look at that. I was talking too much about for the first slides. Anyhow, I will try to keep, let's say, not ignore some slides, but to discuss them a little bit in a more lighter way. The first part, as we indicated, was on the improvement of the development cycle, and this GreenSoft model is basically a sustainable software engineering process. And of course, this process was not developed without any conditions, requirements, and so on. And basically, they also claimed that a sustainable software product meets three conditions. The software is produced in a way that meets sustainability goals, so we have to reduce also energy consumption during development. Software has a minimal negative social and environmental impact. That's called first order effects in here when it is executed, more or less. And the software functionality reinforces sustainable development, or at least have no impact on society or the environment in here, which is then the second order or systemic effects we might have in here directly. And when dealing with development, of course, we should have these conditions in mind, and therefore they're mentioned in here. The process, and as I said, I will not go into detail, has more or less considers four parts. One is life cycle of the software product. The other one is the sustainability criteria matrix, which is important, of course, because usually sustainability criteria matrix, they are always steering or used to control processes in software engineering. So they are a must in here. Then, of course, there is this procedure models on how development, purchase, administration, and use is carried out, but because this has also an impact on sustainability. And then there is a need of recommendations and tools during this process for the developers, administrators, of course, for purchasers, for users, in order to use software in a way that minimizes impact on emissions. There is, and this is maybe the interesting part here. In this process, the authors introduced a quality model for sustainable software, and this includes, on one side, I'm jumping in here, efficiency, so random efficiency, for example, or CPU intensity, memory usage. This has, of course, an impact on the energy consumption, and this is something we may want to avoid or reduce at least. There are some other things like product sustainability, which has to do with fit for purpose, maybe the beauty, the how to say, a user interface that is easily for users to work with, and all these things in here. Of course, in the process, there are also some directly related criteria like traveling, the carbon footprint of environment of the development environment in this case, the energy consumption that occurs during that, and other things in here. And what this model basically is, the quality model is saying that we need not only the efficiency, reusability, modifiable, and usability as quality aspects, which and correctness, I would say, because I'm usually working on safety critical systems, so this is also important. But sustainability should also be one of the quality aspects we need to consider. There are several categories when we go to the process-centric software sustainability. There is a management process where sustainability plays a role. I will not go into detail here because of time. There is sustainability in the engineering process, and then finally in the qualification process, where the other one deals with external resources for engineering, management support, and all these things in here. In all these processes, sustainability needs to be introduced as an additional requirement, and so to speak, the environment would be then one of the stakeholders that we should also consider in the engineering process. In that way, it would be easily integratable in software engineering as well, which is a good thing to have. Of course, there might be also some agile and sustainable software engineering things in here where we have activities like process assessment, focusing on sustainability in there. So where we have a look at the used carbon footprint during development as well. We may add their sustainability reviews and previews in this part, not only functionality, what is usually done in agile processes, but to also add here sustainability as one of the factors. And when you want to introduce that into agile processes, there are three additional roles, like the customer representative development team, a sustainability executive, where the last one is the one. There's only one that is added. I was wrong here, but the sustainability executive will be added in here, and such a position would take into account also having the role of decreasing, let's say, at least the effect of development for the environment. Okay, so this was more or less the process. The question is now, can we do better? Can we, let's say, come up with sustainable software, which means a software that has a reduced carbon footprint using automation? That's always the holy grail. So maybe it can be solved now because many people are now going, to large language models and using them for programming. And personally, I have to say, I was not aware, or was not aware. If you would have asked me 10 years ago, could programming be automated soon? And soon means within the next 5 to 10 years, I would have said, no, I don't believe that. Anyhow, with large language models, to some extent, this can be automated now. The question is whether this can be also used for sustainable development or for the development of sustainable products then. Would be an interesting question. I have no clue about that, and I'm not sure whether there are a lot of publications around, but I'm sure people work on that at the moment. But yeah, it would be interesting to see whether there are tools and whether we can do better by tool support. Because if you have tool support for coming up with the final product, the program, which is the outcome of software engineering, basically, besides other artifacts, of course, then it would be great to have such tools. And what I want to talk about is here one publication, which is quite an interesting one about genetic improvement. I have a lot of slides about genetic programming, which I will pass very quickly because, as I said, lack of time in here. But the idea here is quite easy. It's saying, okay, let's have a look at the product. And of course, we know now that when you run a program, it takes time. And because of taking time, it takes computational resources that lead to basically less maybe energy or more energy consumption, and to have an energy efficient software would be great in here. So it would be nice to have at least tools that guide the user to energy inefficient areas of software. And when we can automate that, that would be the more or less the holy grail what we have in here. And with genetic improvement, which is basically the application of genetic programming, that would be maybe a solution to that. How can this be done? You have a program P, like mentioned here, with a lot of test cases, which are marked here, which are passing and failing. Hopefully, finally, before shipping out, most of them, or the importance at least, to pass. And then you have for all these tests energy consumption. Then it would be interesting to apply changes to this program, leading to a program P prime that behaves like P, but having a lower energy consumption in here. So this is the underlying idea, and genetic programming, search-based software engineering to some extent may be used for that. What is genetic programming? It's easily explainable. You have, yeah, like we have in nature, you have a population that is more or less determined by chromosomes. You have the chromosome store, how this element of a population looks like. Finally, we have this here as well in our pool of humans and let's say other animals in here. So we have this here, and then there are selection operations on fitness functions. So some elements of the populations have a higher fitness value than others, and via crossover and mutation we can change that, leading to new populations. The fitness function then will be used to more or less steer then this process into an area where we have optimized an optimized outcome. Mutation and crossover, I don't think that I need to define in here. Crossover would mean that we take some parts from one chromosome and map and other parts from another one, and then generate a new element of the population. Mutation means that we change here only maybe one part of the chromosome in here. And when we apply crossover and mutation to some extent over the populations, over the years, then and then apply the fitness function, then the number of fittest population elements should be increasing. This is the idea in here. Fitness function is basically taking a chromosome and leading to a value. I'm here very fast now. And basically the algorithm is easy. It's initializing a population, select the best things out there using a fitness function, performing crossover, performing mutation on the population, then having a look whether an element of the population already is good enough. If not, then we select again elements of the population using the fitness function and perform crossover mutation again. So this is the thing we have in here. How can this now be used for programming to reduce energy consumption. There was a nice paper by Bruce Betke and Mark Harman. He is a very famous guy in software engineering, coming up always with interesting and nice ideas. If you want more, I would recommend reading this paper. It's um, uh, one paper showing how programming or how genetic algorithms can be used to change the program, but focusing in this time on making a better program in terms of energy consumption. So what the authors suggested was to add the energy consumption and the fitness value, but maybe also some other aspects like passing and failing test cases. And what they did basically is they used Minisat, that's a SAT solver basically, as for a study, for initial study, and they wanted to, yeah, come up with mutations of Minisat so that they are let's say, better in terms of their energy footprint. So less energy consumed for SAT solving. So this was the idea. In the text, there is a little bit more information, but let's go to the results. They implemented, of course, crossover and mutation as well. Again, I don't want to go into detail. What they carried out was an experiment, and I think this is the interesting thing. As I said, Minisat, and they used some constraints system to be solved for Minisat, CIT, ensemble, proof. And they were, of course, also having coming up with test cases on that. Then they used, and this is some tools for energy consumption. There is an Intel Power Gadget API for macOS, at least in the old times for Intel Core processors. I have to look whether similar things are available for M1 or M2, so the new processors in here. And those things can be used then to estimate at least the total energy consumption. The results are quite interesting, I would say, for the different applications. The reduction is different. So there was the ensemble constraint problem where the reduction was the highest. So we see here always a lower energy footprint in here. And this is also very well visible using the box plots diagrams in here. But the average reduction is not always that good. In addition, they also applied that, and this is an interesting thing in more or less. So they used CAD for optimization, and then they applied it on ensemble or a proof. In this case, they received a timeout, so it was not able to make to come up with a solution for those systems in here. But the interesting thing here is for a proof, when they used it on CAD and on ensemble, they were still able to have a small reduction. But can we optimize for one SAT application the use of another? The answer is most likely not. So all the optimizations they were delivering, unfortunately, were not good enough for all the programs, which is a pity, I would say. What's interesting is the energy consumption versus runtime. So it's more or less something linear in here. So what we see here is all the findings show that CPU-bounded processes such as Minisat optimize execution time exclusively, producing more energy-efficient solutions. And this is the interesting part in here, that all the reductions were more or less based on reducing the necessary steps in here. So I'm running out of time, so I come to the conclusion. Sorry for that. We discussed what sustainable software engineering is, what green software is. We focused basically on sustainability of the generation of software, discussing basically these different parts, development versus execution. We also discussed first programs, basically genetic improvements that help to come up with green software automatically, but we also see that this is not a final solution, unfortunately. So there is still research required. It's also interesting that there are many facets of sustainable software engineering. I would say it's not a common agreement, but there is a large agreement on that, but not a complete agreement on that. Basically, it means on one side finding better, less resource requiring programs. It may mean also improving the development process in here. Um, Anyhow, we need to reduce runtime so that we can, in this case, always reduce also the energy consumptions, and so on. Genetic improvement can be used for that purpose. So this is also interesting. The use of LLMs and other deep learning techniques or whatever would also be interesting to investigate. So these are some open research challenges we should tackle. And if you're interested in the current state here, there is a workshop series, and the interesting thing is it was between 12 and 18, the International Workshop of Green and Sustainable Software, as part of the main conference in software engineering, the ICSI conference series. But then there was people were not interested in that anymore for 5 years, but now since 2023 they restarted that, and with the goal of green software engineering, apply green principles to design and the operation of software. And with that, I conclude my presentation, and I'm open for questions in here.